All right, in this video, we're going to talk about the last section in chapter 7. That's section 7.3, using algebra tiles. Now, this is pretty much a manipulative that is used to represent algebraic equations. And here we can use what they call algebra tiles to represent equations and also solve equations visually. Okay. So we'll start with the linear equations with one variable. And of course, a linear equation with one variable is an equation that involves one variable, such as x, that has an exponent of 1. Okay, the variable could be any letter, like n or m or x, y, or z, does not matter, as long as the exponent, the highest exponent, is a 1. We usually solve an equation by transforming an equation into a simpler one that we already know how to solve. Okay. Now, a linear equation may have one solution, infinitely many solutions, or no solutions. Okay. Now, this is just the expectation for students here. They should be able to give examples of linear equations with one variable, with one solution, in infinitely many solutions or no solutions, and show which of these possibilities is the case by successfully transforming the given equation into simpler forms until an equivalent equation of the form x equals a, or a equals a, or a equals b results. And a and b are different numbers. One and two-step equations are two of the simplest types of linear equations in one variable. Okay, like this one, 2x equals to 12 is a one-step equation because all you have to do there is just one inverse operation. In this case, to solve for x, we're multiplying by 2, so the opposite would be to divide both sides of the equation by 2. And that would give you x is equal to 6. Now, for a two-step equation, you have to do two inverse operations to solve for x, like negative 4x plus 2 is equal to 8. So we start by undoing either addition or subtraction. And in this case, we're going to undo addition by subtracting 2 on both sides of this equation. So that means we're going to have negative 4x is equal to 6. And then we're going to divide both sides by negative 4. That's the opposite of multiplication. You'll get x equals 6 over negative 4. And if you write that as a mixed number, it will be negative 1 and 1/2. Now, we use symbolic algebra to solve one and two-step equations, okay? In this section, you're going to get the skills needed to help your students visualize and solve linear equations using manipulatives called algebra tiles. So that's what this whole section 7.3 is going to be all about, using algebra tiles to visually solve linear equations. So here we're going to model whole number expressions with algebra tiles. Okay, so the algebra tiles that you see here are suitable for solving equations that are restricted to whole numbers. So here is how we represent n and 1. The rectangular tile that you see here is called the n tile. That represents a variable n. And it's not just limited to n, it can be x or y or m. It could be any variable, any letter of the alphabet. And the square tile that you see here represents the 1 tile. Okay. That represents 1 unit. Okay. So on this next page that you'll see here, you're going to see that we want to represent each algebra tile model with an algebraic expression like this one. Here we've got 3 square 1 tiles. That represents the number 3. And then part B, we got 2 rectangular tiles. Those are your end tiles. So here you got 2 end tiles. That represents the expression 2n. Now in part C, you got 2 end tiles and 1 tile. That's 2n plus 1. That's the algebraic expression for that representation. And then in part D, here you got 3 end tiles and 2 1 tiles. This represents 3n plus 2, as you can see here. All right, next we're going to use algebra tiles to model each expression. Like in part A, 3n plus 1. For the 3n, we're going to need 1, 2, 3. 3 end tiles. And for the plus 1, you need 1 tile. This is the representation of 3n plus 1. Now for part D, 5n plus 6. The 5n means you need 5 end tiles that you see here. The plus 6 means I need 6 1 tiles. So that's the representation of 5n plus 6. Part C, 2n plus 5. The 2n means I need 2 end tiles. The plus 5, I need 5 1 tiles. So that's the representation of 2n plus 5. Now look at part D. We got 2 times the quantity n plus 3. Let's represent the n plus 3 that's in the parentheses. That n means I only need 1 end tile. The plus 3, I need 3 1 tiles. But this 2 on the outside of the parentheses means I need 2 of these representations of n plus 3. So I need 2 representations of an end tile and 3 1 tiles, as you can see here. So this is 2n plus 3 as this representation. Now you could use a distributive property here to say 2 times n, that's 2n, plus 2 times 3, that would be 6. That would represent 2n plus 6. So you'll see I had 2 end tiles and 6 1 tiles. Part E is the same way. 3 times the quantity 3n plus 4. Let's represent 3n plus 4 first as 3 end tiles and 4 1 tiles. The 3 on the outside means I need 3 sets of these, as you can see. So I need 3 sets of 3 end tiles and 4 1 tiles. Now, if you did the distributive property, 3 times 3n would be 9n, plus 3 times 4 would be 12. So this would represent 9n from the 9 end tiles, and then plus 12 1 tiles for the plus 12. Now let's try to solve whole number equations with algebra tiles. That'll be the next thing we'll talk about here. The concept of equality is central to algebraic thinking. So here we split a rectangular mat in two halves, as you can see here in this illustration. Here we have a rectangular mat that's going to be split into 2 halves. Each half of the mat represents one side of the equation. Okay, and that splitting line that you see here represents the equal sign. So the tile mat that you see down here represents a 2-step equation for 2n plus 1 equal to 7. The left side of the mat represents the 2n plus 1, as you can see here. 2 end tiles plus 1 tile. The right side of the mat represents 7. So you have 7 1 tiles for the number 7. Now here we can apply the one-step procedures to solve the two-step equation 2n plus 3 equals 11 with algebra tiles. So on the next slide, now this is not the best looking one, but you can see that this is what 2n plus 3 equals 11 looks like and how we can solve this, okay? So we sketch the algebra tiles and write the corresponding equation. So here, 2n plus 3 is equal to 11 is this first one right here. 2n tiles and 3 one tiles on the left, and then you have 11 one tiles on the right side. Then the next line, notice that there are 3 x's here. That means we're xing out those 3 one tiles. We're subtracting 3 on the left side. If we do that on the left side, then on the right side, we need to x out 3 one tiles. Okay, so what we do on the left side, we have to do the same thing on the right side. Then on this next row, you'll see that you'll be left with only 2 n tiles, and on the right side, you'll be left with 8 one tiles. That represents 2n equals 8. And then this next one, we're going to divide by 2, okay? Because there are 2 n tiles here. We need to divide this evenly. That means we need to divide the right side evenly. So that way, each n tile will have the same number of tiles. So to divide this out evenly into 2 groups, each group will have to have 4 one tiles for 1 n tile. So here, this represents the n equals to 4. And we can check our answer to see that 2 times 4 plus 3, that does give us 8. 8 plus 3 is 11. So n is equal to 4 is the solution to that two-step equation that you see here. All right, so next we'll look at this first problem on page 403 in your textbook, A and B. Here we want to write the equation represented by the tile model. So let's look at part A. On the left side of this mat, we got 2 n tiles and 3 one tiles. That's going to be 2n plus 3. The right side, we got 1 n tile and 7 one tiles. That's going to represent n plus 7. So this is our equation. 2n plus 3 equals n plus 7 from this particular model. Okay. Now part B looks like this. You got 2 n tiles. That's 2n. On the right side, you got 6 one tiles. That's 6. So that's just simply the equation 2n equal 6. So that would be the equation represented by that tile model. Okay, let's look at problem number 2 on page 403 in your textbook. Here we want to represent each equation with a tile model. So in part A, you got 3n plus 1 is equal to n plus 5. Part B, 2n plus 1 is equal to 7. Let's look at part A. This is what 3n plus 1 equals to n plus 5 looks like. 3n means you've got 3 n tiles. The plus 1 is one tile. This vertical bar represents the equal sign. For the n plus 5, we need 1 n tile plus 5 n tiles. Now for part B, 2n plus 1 is equal to 7. Looks like this. For the 2n, that's 2 n tiles, as you can see. Then plus one tile, that's this right here, that's 2n plus 1. This is equal to 7, means 7 one tiles, as you can see here. Here's a few examples where we're going to use algebra tiles to solve the following equations. Like in part A, you got 2n plus 5 equals to 9. Part B, 3n plus 2 is equal to 14. And part C, 4n plus 1 is equal to 13. Let's start with part A. 2n plus 5 is equal to 9. To represent that, we need, for 2n, 2n tiles. For the plus 5, 1 tiles. And then that's equal to, that's where this vertical line comes in, 9. We need 9 1 tiles, like this. Now for the next match, that looks like this. Notice I put X's over those 1 tiles. That means I'm subtracting those 5 1 tiles on the left side. And if I subtract 5 1 tiles on the left side, I need to subtract 5 1 tiles on the right side. That's the 2n plus 5 minus 5 equals 9 minus 5. And then next, I'm going to be left with just 2 n tiles on the left side. And if I eliminate those 5 1 tiles on the right side, I'll be left with 4 1 tiles. So that's 2n equals to 4. Now here, I need to divide by 2. Okay. For every 1 tile, I want to divide this evenly into 2 groups. Those 4 tiles need to be divided evenly into 2 groups here. For one of these, I need 2 of these. For one n tile, I need 2 1 tiles, as you can see. So on this last line, you'll see that n is equal to 2. And that's how we represent algebra, solving an algebraic equation using algebra tiles. Okay. Now let's look at part B. Okay. Here we go. This is 3n plus 2 equals to 14. So here's how I represent 3n plus 2 equals 14. The 3n, I need 3 n tiles, plus 2, I need 2 n tiles. 2 1 tiles. And that's equal to 14. You can see I need 14 of these 1 tiles here in this case. And then next, to get 3n by itself, I'm eliminating 2 n tiles on the left side. If I do that, I must eliminate 2 1 tiles as well. 2 1 tiles eliminated on the left, and 2 1 tiles must be eliminated on the right. That represents a 3n plus 2 minus 2 is equal to 14 minus 2. So I'll be left with just 3 n tiles on the left side. Eliminate those 2 n tiles, I'll be left with just 1 tiles. 2 1 tiles eliminated on the right side will leave me with 12 1 tiles. 3n equals to 12. And now we divide both sides by 3. Well, for every 1 tile, I need to divide those 12 equally into 3 groups. So I have to do this. For each group, for each 1 n tile, there must be 4 1 tiles. So that represents n equaling to 4. Okay. All right. Now, let me scroll down here to part C. We got 4n plus 1 is equal to 3. 4n plus 1 is equal to 3. So here for 4n, I need 4 n tiles. And for the plus 1, I need just the 1 1 tile. the right side, 13 means I need 13 of these 1 tiles, as you can see. Now, on this next mat, I X'd out one of the 1 tiles on the left. I must X out one of the 1 tiles on the right side. That represents 4n plus 1 minus 1, equaling the 13 minus 1. I'm subtracting 1 on both sides. So I'm subtracting or taking away one tile on each side. So this is what I'm left with. 4n tiles, that's 4n, equaling the 12 1 tiles, that's 12. 4n equals 12. Now we divide both sides by 4. And as you can see here, for every 1 tile, I need to divide 12 of these 1 tiles equally into 4 groups. So each group will have 3 1 tiles. So n equals 3, as you can see down here. Okay. So that's how we use algebra tiles to represent and solve equations visually. And you can also use that with your students to help them with algebra. All right, let's talk about integer expressions with algebra tiles. So now we can use algebra tiles to solve equations such as 3n plus 5 equals n minus 1. Like the chip model for integers, we need 2 colors to distinguish positive and negative integers. Okay, since we're doing this by video, notice that the unshaded or the white rectangle represents the n tile, the black represents negative n. The square, the white square represents 1, the black square would be negative 1. Okay. There are some algebra tiles that you can use that have different colors, like I think the green represents a positive n tile, or positive n or positive 1. The red will represent something negative. The red could be a negative n tile or a negative 1 tile. Okay. Here's how we model 0 pairs. Usually a white and a black together will give you a 0 pair. So an n and a negative n makes a 0 pair. 1 and a negative 1 also makes a 0 pair as well. So here there are multiple representations of 0 in the model, much like the chip model or the charged field model for integers. Usually a chip model could be something like a red and a blue chip, or a red and a green chip. The red could be negative, the green could be positive. The charged field model could be something like this. A positive charge is positive, the negative charge will be negative. Okay. So a positive and a negative charge gives you a 0 pair. So let's look at this. Let's say we want to sketch the tile model for each algebraic expression, like 2n minus 3 and negative 4n plus 5. These are parts A and B. So in this case here, for the 2n minus 3, you're going to get something like this. 2n tiles like this, and then we could write negative 3 as plus negative 3, so that means they're going to be 3 black 1 tiles for negative 3. Okay, because we can express 2n minus 3 as 2n plus negative 3 by adding the opposite. And in part B, we got negative 4n minus 5 and that can be expressed as negative 4n plus negative 5. So for the negative 4n, that'd be 4 black 1 n tiles, And then for the -5, 5 black 1 tiles. That's your representation of 4n, -4n minus 5. All right, now let's say in this case, we got we have this problem number 4 on page 403. We want to use algebra tiles to represent each expression. Like in this case here, let's start off with a 3n minus 1. I can write that as 3n plus -1 and represent that using algebra tiles. The 3n represents means I need 3 white n tiles. The plus -1, well, that -1 means I need a black tile to represent a black 1 tile to represent -1. Now part B, -3n minus 2. Now that can be written as -3n plus -2. Now for the -3n, I need 3 black n tiles and 2 black 1 tiles for -3n minus 2. Now for the 4 minus n, I can write that as 4 plus -n. For 4, I need 4 white 1 tiles for +4. For the -n, I need a dark n tile or black n tile for -n. All right, let's look at problem number 3 on page 403. We want to write the equation represented by the model. Take a look at part A of that model. You got 2 white n tiles and 2 black -1 tiles. So that represents 2n minus 2 on the left side. And then that's going to be equal to, you got 1 black n tile for -n and 7 black tiles for -7. So this will be 2n minus 2 equals to n minus 7. And then part B, on the left side, you got 4 black tiles, 4 black n tiles for -4n, and then 6 white tiles for the +6. Then that's equal to, on the right side, 1 white n tile for n and 4 black tiles for the -4 or -4. So we got -4n plus 6 equals to n minus 4 as a representation for that tile model. Okay. Let's look at problem number 5 on page 403. Here we want to use algebra tiles to represent each equation. So in part A, we got 1 minus n is equal to 2n minus 5. Let's look at that one. Now here I could write 1 minus n as 1 plus -n, and 2n minus 5, I can write that as 2n plus -5 and represent that in a model. The 1 means I need 1 white 1 tile. The -n means I need 1 black n tile for 1 minus n. And then that's equal to 2n plus 5. Or that 2n, I need 2 white n tiles for 2n. And I can write that as plus -5. That means I need 5 black 1 tiles for -5. So that's the representation of 1 minus n is equal to 2n minus 5. Now, in part B, you got 2 times the quantity 1 minus n, and that's equal to 5n plus 7. Here's what that representation looks like. Let's work with the 1 minus n as 1 plus -n. That means I need one white one tile and one black end tile. But the 2 on the outside means I need 2 sets of 1 plus negative n. So here's the 2 sets of 1 white tile and 1 black tile, 1 black end tile. Then that's equal to, now for the 5n plus 7, that's simple, 5 white end tiles and 7 white one tiles. So that's the representation of 2 times the quantity 1 minus n equals to 5n plus 7. All right. Now let's briefly talk about solving integer equations with algebra tiles. Here the tile model for solving 1 and 2-step equations with integer mimics the model for 1 and 2-step equations with whole numbers. So we use the tile model to solve a multi-step equation involving integers. The next example relates the symbolic approach to solving an equation and the corresponding actions in the tile model. And here is that representation here. Okay. So here's that representation here. As you can see, I have 2 white end tiles and 1 black tile. That's 2n minus 1. The right side is the 1 black end tile and 7 black one tiles. That's negative n minus 7. So the equation I'm trying to solve is 2n minus 1 is equal to negative n minus 7. Now, here's step number 2. As you can see here, I'm adding 1 white end tile to each side of this equation because, as you're going to find out in this next step, I'm going to create a 0 pair. Okay, so that represents 2n minus 1 plus n equaling to negative n plus 7 plus n. Here I'm adding n to both sides of the equation in order to get the variable on one side. Now in step number 3, you're going to see that 1 black end tile plus 1 white end tile represents a 0 pair. So I'm going to have 3n minus 1 here, and then that's going to be equal to, and I'll be left with only 7 negative 1 tiles. That's negative 7. All right, next. In step number 4, you're going to see here, I added 1 white tile to both sides because I want to create a 0 pair here to get 3n by itself. That represents 3n minus 1 plus 1 equaling to negative 7 plus 1. I'm adding 1 to both sides. So I add 1 tile to each side of the equation. Now, on this next slide that you're going to see is where a black and a white one tile form a 0 pair. I'm left with 3n tiles. That would be equal to, now on the right side, I have a 0 pair as well, a black and a white. That forms a 0 pair. I'm left with only 6 negative 1 tiles, or negative 6. So that's 3n equals negative 6. Here we divide by 3, okay? We're dividing each one of these n tiles by 3. We need to divide those 6 negative 1 tiles evenly in groups of 2. So n is equal to negative 2. So that's how we use integer. We can solve integer equations using algebra tiles. And also that's where the 0 pairs come in. Now problem number 9 on page 404. Now I had this spread out in 5 different slides here for parts A, B, C, D, and E. Here, each map represents steps in solving a multi-step algebraic equation. You want to write the corresponding equation for each map to determine the solution and then check your answer. Okay, so in part A, this is what the map looks like. So notice I got 3 n tiles, that's 3n, and 7 1 tiles, plus 7. The right side, I got 1, 2, 3, 4 n tiles, that's 4n, and 1, 2, 3, 4 1 tiles, that's a plus 4. So that first equation that I'm trying to solve is that 3n plus 7 is equal to 4n plus 4. Now, the next slide is part B. Notice that I X'd out 3 of the n tiles on the left side. And if I do that on the right side, I also have to X out 3 of those n tiles as well. So this represents 3n minus 3 plus 7, and that's equal to 4n minus 3n plus 4. Now part C looks like this. After subtracting 3n on both sides, I'm left with this. I'm left with 7 1 tiles, that's 7, and that's equal to 1 n tile, that's n, and 4 1 tiles, that's plus 4. So the equation there is 7 is equal to n plus 4. Now part D looks like this. Notice that I X'd out 4 of the 1 tiles on the left side, and I also have to X out 4 of the 1 tiles on the right side in order to get that 1 n tile by itself. So that's going to be 7 minus 4 is equal to n plus 4 minus 4. And then finally, I have this. 3 1 tiles, that's 3, equals to 1 n tile, that's n. That represents 3 is equal to n, or n is equal to 3. So here's just that one problem that's separated into 5 different slides. Okay. In this example, if we want to solve 3 times the quantity 2n minus 1 equaling to 2n plus 9 using algebra, we want to relate the symbolic action to the tile model, like in this case here. Now, as you can see, in the first step, we represent the equation with algebra tiles by placing 3 groups of 2 n tiles and 1 -1 tile on the left side of the mat. Place 2 n tiles and 9 1 tiles on the right side of the mat to represent this symbolically. Then step number 2. There are 6 n tiles and 3 -1 tiles on the left side of the mat. That's 6n minus 3, where they use the distributive property. And then on the right side, you got 2 n tiles and 9 1 tiles on the right-hand side of the mat. And then this is step number 3, where they added 3 to both sides. You add 3 1 tiles to both sides of the mat. And then on the left side, you'll be left with 6n minus 2 is equal to 12. That's step number 4. You're going to remove all 0 pairs and combine the 1 tiles. Because minus 3 and a plus 3, they form a 0 pair. 9 plus 3 gives you 12. Combine the 1 tiles. And then step number 5 is this step. Take away 2 n tiles from each side of that mat. So when you do that, you're left with 6n minus 2, and you're going to be left with 4 n tiles on the left side is equal to 12. That's where you simplify. And then you're going to divide each side into 4 groups. So that means n will be equal to 3. So when you divide each side into 4 groups, you're going to divide both sides of this equation by 4 to get n is equal to 3, meaning 1 n tile will be equal to 3 1 tiles. And of course, you can check to see if the left side equals the right side. So on the left side, this represents the left side. 3 times the quantity, 2 times 3 minus 1. 2 times 3 is 6. 6 minus 1 will give you 5, and then 3 times the 5 will give you 15. This represents the right side, 2 times 3 plus 9. If you do 2 times 3, that's 6. 6 plus 9 is 15. So that solution would be n is equal to 3. The left side equals the right side of that equation. Let's say we want to use algebra tiles to solve 5n plus 2 equals 3n plus 8 and show the corresponding algebraic representation. And here it is. For the 5n plus 2 is equal to 3n plus 8, you're going to need 5 n tiles, as you can see on the left side, and 2 1 tiles on the right side. This vertical bar represents the equal sign, 3n, 3 n tiles, and 8 1 tiles for 3n plus 8. And then we're going to solve here. In this case, we're going to need to X out 3 n tiles on the left side and 3 n tiles on the right side, because I'm going to collect all the variables on one side. So that represents the 5n minus 3n plus 2 equals to 3n minus 3n plus 8. Here, I want all the variables on preferably the left-hand side. So for this next representation, you'll see I'll be left with 2 n tiles and 2 1 tiles for 2n plus 2. Then that's equal to only 8 1 tiles for 8. Now, get rid of the 2 1 tiles by Xing out 2 n tiles on each side. That represents 2n plus 2 minus 2 is equal to 8 plus 2. 8 minus 2. So you'll be left with 2 n tiles for 2n, equaling to 6 1 tiles for the number 6. And now we're going to divide those 6 1 tiles into 2 groups. Okay, so each one of these 1 tiles will have only only one of those n tiles will have 3 1 tiles. So that's n is equal to 3. 1 n tile for 3 of the 1 tiles. Okay. Let's see, and finally, problem number 6 on page 403. I'm thinking of a number. If you multiply it by 5 and add 3, then the result is 23. What equation would you use to solve the problem? And what is the number? In this case here, this is one of those word problems where you may have to assign a variable and then translate that sentence into an equation. So in this case, I'm letting n be a number or the number that I'm looking for. Now it says here, if you multiply it by 5 and add 3. So an algebraic expression for that would be 5 times the number n. And then if I add 3, that'd be plus 3. Then the result is, which is your equal sign, 23. So the equation that I would use to solve this problem would be 5n plus 3 is equal to 23. And then we solve the equation to find out what that number is going to be. Well, let's undo addition first by subtracting 3 on both sides of this equation. So you're left with 5n equals to 23 minus 3, which is 20. Now, to find out what n is, I'm multiplying it by 5, so I need to divide both sides by 5 to get n is equal to 4. Okay. All right, so this does conclude this video on Algebra Tiles, which is section 7.3. The homework will be available on WebAssign for you to complete. And also, do feel free to email me if you have any questions about anything that's in this particular section. Okay.